Hey guys, today we're going to continue on with our homologous series stuff. Now it's the same syllabus outcomes, so feel free to read through that. But basically today we're going to move on to a lot of the physical properties within homologous series. So let's have a look at revision. So a homologous series is a series of compounds with similar chemical properties differing from the successive member by CH2. So remember it was something like methane, ethane, propane, going CH4, C2H6, C3H8, so going up by CH2 each time. Now, the orbitals around carbons are hybridized, which affects the shape. Now, we need to know the shape because it affects reactivity. The important ones are that single bonds produce tetrahedral shapes, double bonds produce trigonal planar shapes, and triple bonds produce linear shapes. So let's have a look at the properties of homologous series. So the chemical properties of molecules in a homologous series are all very similar. Chemical properties are determined by the functional group, and because all molecules in a homologous series have the same functional group, they should have same chemical properties. Now, the physical properties of compounds in homologous series are determined by the intermolecular forces that are present in the molecule. So, before we get on to how it affects it, let's just revise some intermolecular forces stuff. Now, we did this in module 1 way back when, so these are just the same slides that I used then, but hopefully it'll remind you of the forces that occur between molecules. There are three main types of intermolecular forces. We have dispersion forces, aka van der Waals forces, dipole-dipole interactions, and hydrogen bonds. Now, all of these three types of intermolecular forces all rely on electric fields. Okay, and the big thing to remember with electric fields is that the stronger the charge, the stronger the interaction. Okay, the other thing to remember is that positives and negatives like each other, positives and negatives repel each other. Okay, so let's get onto this. Dispersion forces. So dispersion forces, aka London forces, aka van der Waals forces, are small interactions of temporary electric fields created by electrons around an atom. Basically, you've got electrons whizzing around an atom, and at some point what might happen is some electrons might both end up on one side. Okay, so we get what we call fluctuating dipole. So we get this little spherical atom where the charge temporarily builds up on one side. Okay, and it's just a chance that it happens. We then have a second molecule. When it's brought close, those charges affect the charges in the other one. Okay, so the charges in the first, where there's that chance charge separation, will affect the electrons around the second one in that the positive side of the first molecule will draw the electrons towards it, making that side negative in the second molecule. So we have that attraction between opposite charges. That will then affect the third, that will affect the fourth, and so these interactions lead to stronger intermolecular forces. Okay, so from nothing, when there's no chance charge separation, there's no interaction. But when there is a chance charge separation, we get attraction occurring between them. Now, dispersion forces depend on the number of atoms within a molecule. The more atoms there are, the more chance there is for charge separation. If there are more atoms, higher chance that those temporary electric fields will appear. And so this leads to a general trend of higher molecular mass producing stronger dispersion forces. Now, it's not just more atoms, but it's atoms with more electrons around them as well. Now, dipole-dipole. So the London dispersion stuff's temporary. It's actually quite weak. We can have dipole-dipole interactions, which actually arise from polarity created by polar covalent bonds. Now, in all of this organic stuff, we've been talking about covalent bonds where the bonds share the electrons. Remember, sometimes we can have elements with different electronegativities at either end of the bond. So you have something like oxygen-hydrogen or oxygen-carbon producing this polar covalent bond where the electronegativity of one atom tends to pull the electrons towards it, meaning that the electrons spend more time around that one. So each polar covalent bond creates a dipole moment, and so that's what we mean by that charge separation. So for example, oxygen being more electronegative will produce a partial negative charge around it. Now, each dipole moment adds through 3D space to create an overall dipole moment. And it's basically just 3D vector addition. Now, we don't actually have to do any 3D vector addition, thankfully, but that's how it works. Now, when there's an overall dipole moment, the molecule will undergo dipole-dipole interactions. Now, this is what it looks like. So here we've got an example of hydrogen fluoride, so just hydrofluoric acid. Fluorine is very electronegative. And so with that hydrogen-fluorine bond, the electrons spend much more time around the fluorine than they do around the hydrogen. So we basically get this area of electron richness around the fluorine and electron poorness around the hydrogen. So we effectively create a negative charge around the fluorine, a positive charge around the hydrogen. But they're not full formal charges that we're used to dealing with. It's just, it spends a bit more time around the fluorine, so it's slightly more negative, effectively, on average. Now, that negative electron-rich region is attracted to the positive electron-poor region of another molecule. Now, this attraction keeps them together, and is what we call our intermolecular force. It keeps them together. Hydrogen bonding are very similar to dipole-dipole, but it's dipole-dipole that occurs in very specific circumstances and is very strong. And those specific circumstances is when a hydrogen is covalently bonded to an oxygen, a nitrogen, or a fluorine atom. Now, when we get that charge separation, that partial positive, that partial negative, happens to a huge extent. Okay, so we get lots of positive around the electron poor region, lots of negative around the electron rich region. Now, it's still not quite a formal charge, but it's very high. The electronegativity of oxygen, nitrogen, or fluorine, combined with the presence of lone pairs of electrons, creates this super strong dipole moment. Now, when this particular dipole is brought near another that is the same, the intermolecular attraction becomes very strong. So here's an example. Down the bottom, we've got hydrogen bonding between ammonia molecules. So we have a nitrogen-hydrogen bond. That nitrogen's super electronegative, super electron rich, and the hydrogen's quite electron poor. And so we get that attraction between them. Water is very similar. So the highly electronegative oxygen takes all of the electrons, makes it that delta negative. It's attracted to the delta positive of the hydrogen on another water molecule and creates these really strong bonds. And I mean, these hydrogen bonds in water are the reason that we're actually able to use water as a liquid. I mean, it's only got a molecular mass of 18, which is very low, but the hydrogen bonds keep it as a liquid up to 100 degrees. We can see in the third example, HF. So it was the same example that I used for dipole-dipole interactions, but this is just a dipole-dipole interaction on steroids. It's very electronegative on the fluorine, very electropositive on the hydrogen. Okay. Now, the strength. This is the important part. All of the intermolecular forces we've looked at today involve electric field interactions. And as the electric field becomes stronger, so too does the intermolecular force. Dispersion forces. All molecules have dispersion forces. And the strength is about 0.1 to 5 kilojoules per mole. So that's about the energy that you have to put in to break those dispersion forces. So it's not much. Dipole forces, on the other hand, so dipole-dipole interactions, it's about 5 to 20 kilojoules per mole. And hydrogen bonding can go up to 50 kilojoules per mole. Okay, so it's about 500 times, the strongest hydrogen bond is about 500 times the strength of the weakest dispersion force. Now, what is important about that? Why do we need to know these intermolecular forces? Well, it affects the physical properties of our homologous series. Particularly boiling points and melting points are majorly influenced by the intermolecular forces. So the physical properties of hydrocarbons are determined by the size and shape of the hydrocarbons and the intermolecular forces between them. Alkanes are non-polar. So remember, there's no things like oxygen or nitrogen in our alkanes. It's just carbon, it's just hydrogen. There's no real dipole moment. And so the only intermolecular forces are weak dispersion forces. Now, as the length of the carbon chain increases, the strength of the dispersion forces also increases. And this means the boiling point of the alkanes increases with the carbon chain size. It's why, for instance, butane is a gas, propane is a gas, pentane is a liquid with a low boiling point. Same with hexane. Okay, I mean, it's to the point with butane, you can stick it in a good freezer and it should actually turn into a liquid. So here we go. So methane has a boiling point of negative 162, ethane negative 89, propane negative 45, butane negative 0.5. So it condenses at about the same temperature that water freezes at, approximately. Pentane has a boiling point of 36, hexane 69. Now, melting points. Melting points are also affected by the same factors, because remember, for something to go from solid to liquid, it has to start vibrating enough that it can overcome those intermolecular forces and start rolling over each other. And so it follows the same general pattern with a few exceptions. Melting points of straight chain hydrocarbons increase as the number of carbon atoms increase. However, chains with even numbers can pack a bit better in the solid, better than the odd numbers. So this more efficient packing requires a bit more energy to melt the compounds. And so what we get is we get this staggered thing here. So what we've got here is we've got the melting point and boiling point of different alkanes. So we see that methane melts at about, it looks to be about negative 180 and evaporates about negative 160. Most of the first three hydrocarbons all melted about the same point, okay, with propane actually being the lowest. Now again, that comes from the fact that propane actually locks together in a solid better than methane does, and that's why it's slightly lower. But then from there we can see it goes up, across a little bit, up, across, up, across, up. And that would continue a little bit longer. But looking at the boiling points, because boiling points don't have anything to do with crystal packing or anything like that, we can just see that steady increase in boiling point as we're increasing the number of carbons. Okay, so that's a general trend that we have to remember, that as we increase the number of carbons in a homologous series, the boiling point and the melting point increases. Now, solubility. Non-polar nature of alkanes, alkenes, and alkynes makes them insoluble in water. Water molecules are polar and held together by really strong hydrogen bonds. And so the weak dispersion forces between water molecules and hydrocarbon molecules aren't strong enough to overcome the strong attraction between water. So you can kind of think of it as a bunch of magnets, let's say a bunch of spherical magnets in a bucket of marbles. Eventually the magnets, because they've got this really strong attraction to each other, they're going to work their way towards each other. Okay? And regardless of the attraction to the marbles, from gravity, for instance, the magnetic field will pull the other, like the magnetic ones together. And it's the same sort of thing with water and oil. So the water has these strong attractions to each other, which pull them together, leaving the oil just to do whatever. The oil has no particular fondness for each other. It's just that the water has such fondness for other water molecules that they attract each other and come back together. Density is also affected by our intermolecular forces. Hydrocarbons have a lower density than water, so they float on water. And again, water is polar, so it packs tightly together. Whereas our alkanes, they don't have those same intermolecular forces, so it doesn't pull it in as tightly. So hydrocarbons are larger and non-polar, they have weaker intermolecular forces, and so are not packed tightly together. So, Summary. Physical properties of organic molecules are determined by the intermolecular forces. Longer chains within a homologous series have a higher melting and boiling point. And alkanes, alkenes, and alkynes only have dispersion forces acting between them.